Okay, we're now going to look at how GLMs are estimated, and we're going to do that in the likelihood setting. Just a note before we start, I'm going to cover quite a lot of the material in this part of the lecture at a high level. So there's detail in these slides, particularly in the proofs of the asymptotic properties, that's really not necessary for you to know in detail. And in fact, I've put that material in excursus to indicate that it's not necessary and certainly non-examinable. I'm going to try and cover just here the main concepts and principles, and for those of you who are interested, you can work through the detail in your own time if you want to go deeper. Okay, so restricting distributions to the exponential family is important because it allows us to develop a general method for GLM estimation and inference in a likelihood setting. So recall from lecture 2 the concept of a likelihood function, the L of theta given y, which is the density f of y given theta, viewed as a function of theta for fixed y. So essentially, the likelihood function is a statistical model that allows us to write down the probability of any set of observed data as a function of some parameter values. For example, if y1 through yn are IID from some assumed parametric density, the likelihood is the product of the individual densities. Now the maximum likelihood estimator, you'll remember, finds the estimate theta hat at which the supremum of the likelihood function is reached, or equivalently of the log likelihood, since both reach their maximum at the same point. So MLEs are the parameter values that maximize the probability of obtaining the observed data given the model. And it should be clear why this is relevant for GLMs. Our data are distributed according to the random components of a GLM, an assumed exponential family density, so the likelihood machinery is going to carry over directly. So, for a parameter vector theta with k elements, the MLEs are obtained by maximizing the log likelihood. We simply take the partial derivatives with respect to each theta j and set it to 0, giving a system of k equations. These are known as score equations and are defined on the slide. So the score function defined on the slide is the gradient of the log likelihood, the vector of partial derivatives with respect to each parameter. When the response data are independent, both the log likelihood and the score are sums of contributions across observations, and setting the score equal to 0 gives a set of equations whose solution is the MLE, and these are known as the likelihood equations, and that is in essence how we'll estimate GLMs. We'll take the log of the exponential family density, differentiate it, set equal to 0, and then solve those equations. So it's as simple as that. Solutions to the likelihood equations give us maximum likelihood estimates. But the question we might want to ask is, what property do these maximum likelihood estimates have? Well, in general, MLEs are not necessarily unbiased, but they have desirable asymptotic, that is, large sample properties, which explain their widespread popularity. Now, fairly intricate mathematics and statistical theory is required to establish these properties fully. So here I'm simply going to state them, but I've provided some additional detail and outline proofs in the excursus slides that follows, and I'll go through them at a very high level. But I do want you to know this theorem, which is shown here, the asymptotic properties of an MLE. And this says that under certain regularity conditions that concern derivatives of the log likelihood, the MLE has essentially three asymptotic properties. First, it has consistency. So the probability limit of theta hat is the true parameter vector. Second, asymptotic normality. Theta hat is asymptotically normal, centered on the truth, with variance given by the inverse of what's called the Fisher information, which I'll define in a moment. And thirdly, asymptotic efficiency. The MLE attains the Cramer-Rolle bound for consistent estimators. Its asymptotic variance is as small as it can possibly be. So as I said, there is now a proof of those asymptotic properties in these slides, and you follow it if you like. I'm just going to sketch out the idea for you in each of these slides to give you the overall picture. Okay, so slide 1 is on consistency. The key step here in this slide is to use Jensen's inequality, which for a concave log function tells us that the expectation of the log of the likelihood ratio is less than the log of its expectation. The expectation on the right hand side is exactly 1, the integral of a density, and since the log of 1 is 0, we conclude that for any theta other than the true value, the expected log likelihood at theta is less than the expected log likelihood at the truth. In other words, the expected log likelihood is maximized at the true value of the parameters. To complete this proof, we need to apply a law of large numbers. 1 over n times the log likelihood is a sample mean of NIID random variables, so it converges in probability to its expectation. From the previous slide, the expectation we've shown is maximized at the truth, but by definition, the MLE maximizes the sample log likelihood in every finite sample. So the only way both facts can hold in the limit is if the log likelihood evaluated at the MLE converges in probability to the log likelihood evaluated at the true parameters. And that's the point that establishes consistency. Two definitions that have been used in what I've said. First, the Fisher information. The Fisher information about theta is minus the expected value of the matrix of second order partial derivatives of the log likelihood. So the Fisher information is measuring the curvature of the likelihood function near its maximum. And since that curvature is negative at a maximum, we take minus the curvature so the information is positive. To think about this intuitively, the more sharply curved the likelihood is around its peak, the more information the data carry about a parameter. And a useful additional fact is that the covariance matrix of the score is actually given by the Fisher information. Second definition I've used is the Cramer-Rowe lower bound. Assuming regularity conditions on the density, the asymptotic variance of any consistent and asymptotically normal estimator of theta will always be at least as large as the inverse of the Fisher information. So the way to think about this is the Cramer-Rowe lower bound is saying the Fisher information sets the floor on achievable variance. And then finally in this excursus, this slide gives the outline proof that the MLE is asymptotically normal and efficient, again for your own study. The idea is as follows. The maximum likelihood estimate sets the score to 0 by definition, taking a Taylor expansion of the score about the true value and rearranging the estimated error is a ratio. The numerator is the score at the truth, a sum of IID random variables, with mean 0 and variance equal to the Fisher information, so by the central limit theorem, it's asymptotically normal. The denominator, by a law of large numbers, converges to minus the Fisher information. Putting these together, the MLE has asymptotic variance equal to 1 over the Fisher information, which is exactly the Cramer-Rowe lower bound. So the MLE achieves the bound, it's asymptotically efficient. That's what this slide is saying. So now let me return to the main thread and derive the likelihood equations for a JLM. Statistical models based on exponential family distributions provide robust inference in the likelihood setting because they give us general expressions for the likelihood equations, asymptotic distributions for the parameter estimators, and an algorithm for fitting models. For a JLM based on an exponential family distribution, the link G of mu I equal to the linear predictor, we solve for the MLEs via the score equations for each beta j. So the log likelihood for the exponential family density is written on the slide. It's the sum over observations of yi theta I minus b of theta I, here, plus the c terms. Note the notation L of beta. We write the likelihood as a function of beta reflecting the dependence of theta on model parameters through the linear predictor. The likelihood equations for the GLM are then the derivative of the log likelihood with respect to each beta j summed over observations and set equal to 0. Now, to carry out this differentiation, it's useful to bear in mind the mappings at the top of this slide. We get from theta to mu via the first derivative of the function b, and we get from mu to eta via the link function g. So to differentiate the log likelihood, we're going to use the chain rule. The derivative of Li with respect to beta j is the product of 4 terms. The derivative of Li with respect to theta times the derivative of theta with respect to mu I times the derivative of mu I with respect to eta I times the derivative of eta I with respect to beta j. Now each piece has a simple form. From the exponential family log likelihood, the derivative of Li with respect to theta I is yi minus b prime of theta over a of phi, shown here. The derivative of theta with respect to mu is 1 over b double prime of theta, and the derivative of eta with respect to beta j is just xij, since eta is a linear parameter. Now, using the facts that mu I equals b prime of theta I and the variance of yi equals b double prime of theta I times a of phi, we multiply the pieces together. The a of phi terms cancel, and we get the neat expression shown, yi minus mu I times xij over the variance of yi times d mu I by d eta I. So that is this expression here. Now, summing over the n observations yields the likelihood equations at the bottom of the slide. It looks complicated, but all we've done is take the exponential family density, take the log, and apply partial differentiation via the chain rule. Worth working through this in your own time to make sure you're happy with each step. I know there's a lot on this slide, but I think if you sit down and spend half an hour going through this derivation, you'll see that actually it's fairly straightforward. So the complete generalized linear model score vector collects the score equations for each parameter, letting V denote the diagonal matrix of variances for the observations and D the diagonal matrix with element D mu I by D eta I, this thing here. The likelihood equations can be written compactly in matrix form as X transpose D V inverse times y minus mu equal to 0. So although beta doesn't appear in these explicitly in these equations, it's there implicitly sent through each mu I, since mu I is the inverse link applied to the linear predictor. Different links yield different sets of equations, and importantly, the likelihood equations are typically nonlinear functions of beta that must be solved iteratively. There's generally no closed form solution. To achieve this, iterations based on Taylor expansions of the score are applied via 2 methods, one called the Newton-Raphson and one called Fisher scoring. And I'm going to go through the fitting algorithms very quickly. I don't need you to understand these in detail. I really need you to understand the principle, that's all. So let's look first at the problem. The problem is we have a vector of functions s of beta, the score, and we want to find the beta that sets it equal to 0. The Newton-Raphson method uses the principle that the log likelihood can be approximated in the neighborhood of some initial value by its second order Taylor expansion shown on the slide, where the Hessian matrix, the matrix of second order derivatives, is called the observed information. Because the local approximation is quadratic, we can find its maximizer directly, approximate the score linearly, set it to 0, and solve for beta. That gives the update shown at the bottom of the slide. The new beta is equal to the old beta minus the inverse Hessian times the score. And the Newton-Raphson method simply iterates this step from an initial value until convergence. A second method is called Fisher scoring, also known as iteratively reweighted least squares. A drawback of Newton-Raphson is that the Hessian is sometimes close to singular, making its inverse numerically unstable. Fisher scoring replaces the Hessian with its expectation, the Fisher information, which is always positive, giving the update shown new beta equals old beta plus the inverse information times the score. For a GLM, it can be shown that the information takes the form X transpose W X, where W is diagonal with elements given by the square derivative of mu with respect to eta divided by the variance. This allows the iterative step to be written as X transpose WX inverse times X transpose WZ, where Z is a working response constructed from the current linear predictor plus a scaled residual. Looking at the form of that update, it's a GLS estimator, generalized least squares, and since W is diagonal, each step is a weighted least squares solution, hence the name iteratively reweighted least squares. At each iteration, we solve a weighted least squares problem with updated weights. One final point, for canonical links, the Hessian equals minus the Fisher information, and so the Newton-Raphson and Fisher scoring methods are identical. So, let's make the likelihood equations concrete with our three examples. First, the Gaussian response. Yi is normal with mean mu equal to the linear predictor and homoscedastic variance sigma squared. The link is the identity, so the derivative of the link is 1 and the variance function is just sigma squared. Plugging into the general likelihood equations gives 1 over sigma squared, shown here, 1 over sigma squared times the sum of yi minus beta transpose xi times xi equals 0. Ignoring the scale parameter, the left-hand side is the jth element of X transpose Y minus X beta, which is exactly the normal equations for least squares. So for a Gaussian GLM, maximum likelihood reproduces the least squares solution. The linear model drops out as a special case. Okay, second, let's look at the binomial response, where yi is the sample proportion of successes. The mean is pi I, the logistic function of the linear predictor, and it does not depend on ni. The link is the logit. Its derivatives work out as pi I times 1 minus pi I. The variance function is pi I times 1 minus pi I over n minus 1. Multiplying these pieces together, things cancel neatly, and the likelihood equations are the sum of ni times yi minus the logistic function of the linear predictor times xij equal to 0. And then finally, the third one we'll look at is the Poisson response. Yi is a Poisson random variable with mean mu I equal to the exponential of the linear predictor. The link is the log, so g prime of mu I is 1 over mu I. Here. The variance function is mu I and phi is 1. Again, the pieces cancel neatly and the likelihood equations are simply the sum of yi minus the exponential of the linear predictor times xij set equal to 0. So notice the common structure across all three. The observed response minus its model mean weighted by the covariates. My advice for this section is don't spend too much time on the fitting algorithms or the asymptotic proofs that are excursus. What I want you to be able to do is go from the exponential family to the log likelihood to the score equations, and working through these three specific examples I think is probably the best way to make that part of this lecture concrete.